Hi, welcome back. In this chapter, we will recreate the classic game of a snake. We will use our RLPP designer in order to create a simple layout. We will modify it to create a bigger data structure that will be the actual snake. We will create a smaller subclass called the body part, and we will explain the algorithm that will allow the agent to train. Besides that, we will also focus on the development of the actions of the agent and finally on how to represent the state of the environment so the snake can see where and what it's doing. I'd like to take a minute to also introduce you to Patrick Lever and his YouTube channel. So Patrick is a YouTuber who provides machine learning tutorials, and he has started some momentum on the integration of Pygame and PyTorch with his tutorials on how to recreate the game that we are addressing today. Many of the elements that he explains in Deep Learning are actually foundational for the templates that you are using with the RLPP designer. This includes the linear decay of epsilon and also the integration of the training methods that are incorporated and integrated with the neural networks in combination with the library PyTorch. So if you haven't seen these videos, I encourage you to take a look at them. And if you have, then some of the code we're going to be using today will feel familiar, especially because the state representation and the actions are going to be inspired by the way that he presents his work. Let's go now to our working directory. Then let's open a new instance of the RLPP designer. First I need to activate the environment that has the RLPP designer. And once it is activated in my Anaconda environment, I can ask for the RLPP designer to be opened. This will give us access to the graphic user interface, and I can start adding elements right away. Instead of adding all of the body parts that make the snake, we will go to the resolution 32 and bring the body part that represents the first block. And this time I'm going to pick the teal color. I'm going to put it anywhere in the screen. Then we can go to the food items, and I will pick this one and drag it somewhere else inside of the window. The size is a little big, but that's okay. I press to confirm, and then I can go to the export tab and select as AI agents. This will give me access to a config.json file, and I can save it in the working directory. Once I get confirmation from my RLPP designer, I can click OK and close that designer. Let's open VS Code. With the editor open, we begin by setting our metadata processing. I will create a new script called processing metadata. And this program will contain 2 lines of code. From the RLPP designer, we need to import the RL processor. And from the RL processor, which is a specific module dedicated for the development of the game structure in Pygame, especially for AI agents, we can ask for the method map.json. Down here, we ask for map.json, and we pass the config.json file that lives inside of the working directory where we currently are. Then I can run this Python file, and as long as I have my environment active, I should be able to process and create 2 new files. Here they are. Model.py contains the synthetic brain of our agents. It contains the neural networks, which in this case are 4 linear units, which are incorporated inside of a sequential unit and enable the agent to make its decisions. The other file is called rl_output.py. This one contains the game that we just created in the layout. You can see that it contains now additional objects, including a game object, which is the foundational unit of information in the program. All of the other elements are part of that object, and finally the game manager. If we run the program right now, rl_output.py, we will see the same layout that we created in the RLPP designer. Let's modify it. For the first time, we need to work in terms of specific steps with a specific resolution. And this is because in the model of the snake, what we are actually doing is updating the position of the snake by adding body parts. Body parts that have a specific dimension, a specific width and height. I strongly recommend you to pick a sprite, if you happen to choose yours, that is symmetrical or square in the x and the y axis. This will greatly simplify some of the following procedures. However, we will begin by moving the screen parameter to the bottom, and I will create a hyperparameter called the resolution. Let's start this at 0. I need to figure out how wide my sprite is. Even though my sprite came from the RLPP designer with a resolution of 32, full disclaimer is not all of the objects have a resolution of 32. To figure out what the resolution is, we go to the agent, and in the line below, we will print the width of that agent. We do it by asking for the name of that agent, the name of its image, and the method getWidth. Let's run the program once more, and we should get a resolution of 24. If I remember correctly, that was the value. Yes, there it is. Okay, so now that we have confirmed that, we can go back to the top and we can type 24. Once we have this, we create a tuple, an object with two elements inside that represent the total number of body parts that the snake can move from the left to the right, the width, and top to bottom, the height. So for the width, the total will be 26, and for the height, 20. This will give us dimensions that are equivalent in pixels to something around 640 and 480. So this screen disappears in its value and is replaced by dimensions at index 0, which is 26, multiplied by the resolution, and dimensions at index 1 multiplied by the resolution. The body part. As I mentioned, the snake is a special type of data structure because it encapsulates not only one sprite, but a collection of sprites. Let's go to the agent. In here, we will call inside of the reset function that is called every single time that a new episode is created, a set of new variables that will contain versions of a simpler object, which will be a member of the class body part. This one will have the name VP, and it will receive three elements: the position in X of the original head, minus the value of the resolution multiplied by a special factor. The first VP will be the head, so we multiply by 0, effectively turning this value into 0 and keeping the original position in X and Y. Then cell.y minus res times 0. And in this case, we don't need to modify cell.y. It's always the same value for all of the body parts. So BP0 will be the head, 1 and 2 are the elements that follow the head. So this one will have the value 1 and this one the value 2. And finally, we create a new element called the self.body that will contain BP0, BP1, and BP2. That's how we create the body. Now, let's go to the lines before the agent and let's create a new class, starting by a data definition. This is called the body part. The body part, or BP, is defined with the class with the capital B with the same name, and it represents the basic block of information that makes the snake. Let's call it BP, and let's define its constructor. We start with self, and as we previously mentioned, we need to pass the position in X, the position in Y, and also the path to the image that will be representing the way that our body part looks in the screen. The position in X stays as X, the position in Y stays as Y, and the image will be produced by loading from the image module from the Pygame library, the image pad. Let's call it here. Now, because we may need to use it later, let's just store the image pad as an internal component of our body part class. We can call it here image pad. There we go. In addition to this simple collection of attributes, we also need to create a new method called draw, which it's actually already being used at a higher level by the agent and at a higher level by the game manager. So in this case, we need to ask for display.blit and pass two elements, the cell.image and a component called cell.rect. Cell.rect is the hitbox, is the space where the sprite actually lives, and it can be automatically created and read by asking the image for it. So all of the images in Pygame contain a rect component. So we ask for the cell.image and we access the getRect component. Then we need to modify the position of this cell.rect. So cell.rect.center would be equal to cell.x, cell.y. That will move the rect component to wherever it needs to be at the beginning of the program. Now that we have this, actually it's important to pass along with self the display surface, which is the actual screen that is created by Pygame. And with that done, we can go back to the agent. So let's also modify the draw function from the agent, because right now the only thing that is drawn is the first component under which the agent was created. That is just one body part. It looks like a body part, but it's not even that. It's just the sprite for the agent. So we're gonna ignore that. And instead, we are gonna receive display and go through all of the body parts that make the body. So for each of those, we call the draw method and we pass the display. And that's all we need to do. Now, before we leave the agent at this point, it's important to remember that we need to pass the cell.image path, and that is an attribute of the game objects. The agent is a game object and therefore also has it, so we call it image path. There we go. Let's run the program. Let's see where we're at. Oops, I was never not running the program. There we go. Excellent. Now, let's make a quick experiment at this point. If you remember, or you were able to look at previous episodes or previous chapters of our tutorials, I mentioned multiple times that the location of a sprite is in its center. That means that the coordinate x and y has to its left the half of the width of the sprite and to its right half of the width of the sprite. So it's right in the middle. And I want to make a quick experiment here, because if I change the position of this agent from 192 to be in terms of the resolution, so we can set it to resolution times, and the following integer can go from 1 to 26 in the width. Remember, that's the total number of body parts that we can pile or stack in one horizontal line without overflowing the screen. Let's put it at the position 0, and for the position in Y, let's put it at position 5, something like that. Let's run the program once more, and I'd like you to pay attention to what happens to the location of the sprite in the x-axis. Because the position is in the middle, half of the width is out of the screen. So we need to add half of the resolution, and that goes for both elements. So we take resolution, division, division 2, and that means integer division, because the position has to be an integer. If we run it once more, this time we're ready to begin dealing with our agents. Perfect. Now, because we only see one single square, it probably means that the rest of the body is hidden. So let's place the snake at the beginning, the head of the snake, a little bit farther to the right. Now we can see the full body. And let's create a similar calculation for the position of the foot. We take the resolution times, let's say 10, plus half of the resolution. And let's make it symmetrical. Let's do the same for the y-axis. Fantastic. What's next? Now that we have all of the components in place, let's go to the play step method inside of our agent. I want you to notice that all of the interactions of the agent with the environment are internal states. Compared to the game of Breakout, where the ball had to communicate what was the reward or the penalties after losing the game, in this case, the game of the snake has the ability and potential to know how well it's doing by only calculating its relationships with the environment, with the screen. So in other words, we don't have other objects that are responsible to the rewards. It's just the snake. So in the play step method, we need to first analyze the actions. The action will be an integer list represented as a one-hot vector where there is only a single digit 1. Everything else is 0. If we have a value of 1 in the first position, index 0, that means we are going to turn left, or the snake will turn left relative to where it's going. If the position is in the middle, that means go straight or keep your current direction. And if the value is on the right, as you can probably imagine, we need to turn right. So let's ask first if the action is going left. In this case, we will modify the cardinal direction of our snake by using the following variable. So we call it self.cardinal direction index, and we're going to make it equal to itself plus 1, then modulo 4. And actually I made a mistake just now. It shouldn't be positive, it should be negative. So where is this information coming from? Let's go to chapter number 5 in the reinforcement learning playground with Python. And if we scroll down, this is an introduction of agents. We have the following diagram. Our cardinal index direction will have a range of values that go from 0 to 3 because we have 4 components and we start counting at 0. If we are going east, then we are followed by south, west, and north. It's always going to be that sequence. It's standard for our purposes. That will make the code easier to create and easier to debug. So from east, value 0, we go south with value 1. So the cardinal direction goes from 0 to 1, and that's great. So the application of the modulo doesn't modify the value or the operation. But if we are at the position north and we go right, then somehow we need to turn back and go to the value in 0. And we could do it with if statements. That's okay. But there is actually a really nice feature in Python with an operator called the modulo. So the beauty of this modulo operator is that it works in both ways, by adding and also subtracting. So if you are in 0 and you subtract and then apply modulo, then you're going to go back to 3. So in effect, going east and turning left takes you north. So that's what is happening. Now that we have this action, let's create an elif statement and let's ask for the other action, which is towards the right. And that one is positive. Now it's time to apply the algorithm that makes the snake. First, let's create a reference, a new variable for the head. This is self.body at index -1. We are accessing the last element in the list. That's always going to be the head. Then we need to evaluate in which direction we are currently going. So if the self.cardinal direction index is 0, we do something. And we do the same for all of the other 3 cases. So remember that we start with right or east, then south, then west, and then north. If the value is 0, we need to create a new head. And we do that by creating a new body part. Let's call it new BP. And it's going to be set to an instance of the object BP that receives 3 components. the position in X of the head, the position in Y of the head, and the image path of that head. In our implementation, the head looks exactly the same as the rest of the body, so that's why we use it this way. Now, let's copy this and let's propagate it throughout the other pass cases. In the first case, because we're going east, that means going right. So we're going to add the velocity, which in this case is the resolution, because we're moving by body parts, to the position in X of the head. When we go down, it is to Y. When we go left, which is, west, we subtract the resolution, and we subtract the resolution when going north. Now that we have the new body part, it's time to append it. We're going to add it to the collection of body parts that is the snake. So we type cell.body.append, and we append our new body part. And now comes the evaluation and the reward. So we need to ask if the new body part is touching any of the 4 walls, if we are in game over or not. And actually, let's leave that for the next step. Let's first focus on the collision with the food. So we need to ask if the new body part is touching the food. For that, we need to receive a new item over here in the play step, which will be the food. So to ask if the new body part is touching the food, we access the rect component. Remember, that is the hitbox. And the hitbox in Pygame has a special type of method called collideRect that receives another rect component. In this case, that from the food. The food is another game object, therefore has a rect component. And we care that this is not touching the food. Because if it is not touching the food, then we pop or remove the tail. So that the snake doesn't keep just getting longer and longer. So we do this by using self.body.pop and the index of the object that we want to pop. In this case is the index 0. Now, there is another case for this, and it is when the snake is touching the food. In that case, we take the position in X of the food and we randomize it. We're going to take a value that goes from 1 to the total number of body parts that we can pile in the x-axis, that is dimensions at index 0, minus 1. And then we multiply by the resolution. And I believe we should add half of the resolution as well. Let's work on the y case, and it is the same thing. Instead, is dimensions at index 1 and everything else remains the same. Now, if the agent touches the food, we yield a reward. A reward will be set to 10. Let's add 10. And notice that we already have it here. It was initialized. This is an example of an accumulator. So let's just move it all the way to the top so that we can just update it. There it is. So that is the reward. And that is really the only reward that the snake is receiving in the game. That's the main feedback. Then let's ask when the snake loses the game. Right? There is really 3 cases in which the snake can lose the game. So if new VP position in X is bigger or equal than the screen at index 0, then it is one example of game over. Because we have 4 examples, let's put it inside of a variable name. It is called touching right, down, left, up. And down and up use the y-axis, right and left use the x-axis. So down and up use the index 1, and right and left use the index 0 for the screen parameter. In this case, when the snake's body part, the head, is touching the right side of the screen, we know that because the left edge of the head's hitbox is over the right edge or touching the right edge of the screen. That is going to happen only if the body part fully enters that side of the screen. So we will represent that by accessing the rect component, and we want the left edge, the position on the left edge of that hitbox. And if it is going down, then it's the opposite, so it is up. If it is going left, is right. And if it is going up, is bottom. Now that we have these elements, we can cast these questions into integers. Once we have them as integers, we can create a list, touching walls, and we can add the 4 of them. One of the nice features of VS Code is that it allows us to do multiple line copy and paste. There it is. Now, if the sum of touching walls is bigger than 0, that means that we are touching at least one of these walls, and therefore game over, which is the state self.isDead of our agent, is equal to true. And we add a quote-unquote reward that is negative 20. I believe it's negative 20. Let's set it to negative 10. It's equivalent to the reward. Let's move to the next one. The second case is when the snake is touching another part of its body. And for that we use for BP in self.body. Now, the head is always the last element in our list. And there is a nice way for us to take it out. We use the colon symbol inside of brackets. And that's how we tell Python, give me a sublist of the original list that includes all of the elements, but it stops at the last one. It doesn't include this element. And that is going to help us avoid asking the following question for the head. If the new head, which is called new BP, we still have it up there. If new BP is touching, and its rect component using collide rect, the body part, then we also lose the game. So we set the self.isDead to true, and we set the reward as well to negative 10. That's case number 2. And case number 3 happens when the snake stalls and doesn't want to move anymore. Not because he wants to maximize reward, but because he wants to minimize penalties. That's when it just stops touching the edges. So we are going to add a special parameter that will quantify how many frames we have passed. And that is something that I'm going to copy straight from the tutorials from Patrick Lieber. I think that's a really nice statement. And it goes like this. So if self.frames are bigger or equal than 100 times the length of the snake body, then we finish the episode. We say self.isDead is set to true, and we set the reward as well equal to negative 10. There we go. So those are the 3 conditions, the 3 situations that can destroy the agent. Now, let's take a moment to create the parameters that we're missing, because I don't think we have a cardinal direction index yet. We go to the top of the agent class, and in the reset, we're going to add these elements. So self.cardinal direction index starts at the right direction, so that is the east direction, so that's 0. And also self.frames is going to start at 0 every episode. We go down here to the play step, where we were, play step. And at the beginning of each episode, we add to self.frames by adding 1 element. We added 1 more frame. And then the evaluation happens down here. Perfect. Okay, let's see if our script can run. It says we're missing 1 required argument, and that is the food. So we go to play a step, the call to the play step that receives a move, but also now it says we need to pass a food. Now food belongs to a list called self.foods, but right now we only have 1 food item. So I'm gonna just pass the first and only element to it. And that should do the trick, at least for now. Before we make the code more complex by adding malleability or the ability for the agent to select multiple food items, let's make sure it works with 1. So BP object has no attribute up, and that is in line 204. Perhaps it's called top. That's probably why it's not working. Okay, so there is no attribute. Oh, okay. Yeah, no, that's my bad. So this should be part of the rect component. It's not an attribute of the body part class instance. It is a part of the hitbox of that class instance. And I guess it should be top. Yeah. Sorry about that. Let's run it once more. Okay, there we go. And bye-bye, snake. You can see that it's beginning to move to different directions. It's going incredibly fast. I can't even see what's going on. So let's do something about that. To change the rate at which the game happens, we go to the game manager. And there is a parameter there called the clock. So let's use it. We go to the draw method and we use self.clock.tick, and let's ask for 20 frames per second. Actually, 10 frames per second. We can change it at the moment when we start training the agent. Okay, there it is, and the snake starts moving around. Hopefully, whenever it touches the food teleports to a different location and gets longer. So the snake just left and is not ending the episode, so we need to find out what's going on there. Oops, this value should be 0 for the up and the down directions, and should be less or equal, because that is the first pixel to the left and to the top. Because remember, Pygame always renders things from top to bottom, so it's flipped to how we normally think of math coordinates. And yeah, okay, so this time the episodes are ending when the snake touches the edges. Fantastic. So let's keep moving forward. Now that we have a functional game, it's time to work with the state representation. This is one of my favorite parts. Let's go to the getState method. And here, first, we're gonna give access to the food item, one single food item. And then we can talk about the length of our state. So following the tutorials from Patrick Lieber, we're gonna change the state representation to have 11 elements. So we're gonna call give me a 0 for every element in a range that goes or is specified by the total number of world states. I go to the top, and in world states, I change the number 4 for 11. So let's go back to get a state. Let's go back to get state. Now, to create the state representation, we need to inform the agent on which direction in the cardinal coordinates it is going, where is the food, and whether or not there is danger in the direction where it's traveling, whether it is to the left or straight ahead or to the right. So we will need to create 3 elements in here. Let's start with the first one, the cardinal position. And to do it, we start by creating a new array that will be called cardinal positions, and we set it equal to a vector with 4 elements, a list with 4 elements. So we take the cardinal positions, and at the self.cardinal index direction, we set a 1. This is a 1 hot vector. And that's it. Let's move to the second one, and let me add a comment here. Cardinal directions. The next one will be food position. And a problem that I experienced with this particular parameter was assuming initially that 2 variables, is down and is right. Let's put right here. Were the opposite case of is left and is up, which is not necessarily the case, because the food relative to the agent could be in the exact same position. And that is neither of those cases. So we need to address these 2 cases independently. And we do it by saying the food position in X is bigger than the self.position in X. That is to say that if the value in the food is bigger than the position of the head of the snake in the X-axis, the food is to the right. Then something very similar happens in the Y-axis for the down direction. And now, as I mentioned, these two additional cases is left and is up. So in this case, we only need to change the symbol. These, again, would be mutually exclusive cases if they added the equal sign. That is the point that I wanted to make. We have the 4 different cases, and finally we move to the interesting case. That's where the meatballs of this pasta are. This is the dangers around, and what makes this method a little bit more complicated is the fact that the dangers are relative to where the snake is going, right? There's multiple ways to do that. The way we're going to do it is by calling a special method and assign the return for that method to a variable that will be called dangers around, and will be equal to the call to a method called evaluate dangers. So let's create it over here. We create a definition, evaluate dangers, and it takes self. In this case, first we begin by taking the information of the new head, and we do it by calling an edge self.body at index -1. Then we have 4 cases where the danger, sorry, we have 3 cases. So dangers is going to be danger to the left relative to where the snake is, straight relative to where the snake is, and to the right. And this is not a one-hot vector. There can be multiple dangers, right? Depending on where it is. Like imagine if the snake's head was in the corner, then more than one of these would be number 1. So we need to evaluate them separately. We will create 4 different variables: danger east, danger south, west, north. And for the first case, we can call another method that will be called named evaluate point. That is taking the position in X and the position in Y of the head. And the purpose of this is to add an imaginary or invisible head in the direction that is forward or left or right to ask the same question. Would I die or lose the game if my head was in that position? So if we are going east, that means adding 1 step in that direction. And the same happens with the south. But before we do it, I want you to notice here, I'm gonna embed these 2 elements inside of brackets, because now they are a tuple. They travel together and they will be evaluated next to each other. So we have case 2, 3, and 4. So if we are going south, we're still adding to the resolution and the position in Y. If we're going west, is negative resolution, and if we're going Y, is the negative resolution. Now, assuming that this method works fine once we create it, we will put these elements inside of a list. So dangers list will be equal to the 4 different values. Now, the data type that these variables represent is of an integer. So these are integers, where 1 means yes and 0 means no. Now, here comes the interesting part, and we will need to look at our diagram for it. So we're going to run the loop 3 times. And we will begin with a new object called the index that is going to be set to the cardinal direction index. I just saw it right there. -1, always with the modulo, right? Because we want it to be cyclic. So this is a very weird syntax. What's going on? What happens here is basically that if the head or the snake as a whole is going in one particular direction, let's say east, we begin by considering the position that is to the left of that direction. In this case, it would be north. If you're going south, the element to the left would be east. If you're going west, the element to the left of the snake is south, and so on. So that's why we subtract 1, because we're going, actually, this diagram is better, if we're going in the opposite direction. Then we run a for loop that will begin at this direction. We were going east, -1 is north. So we begin at this direction, and then we ask if there is danger there in that particular cardinal position based on what we returned from the variables that we just created and placed in the list dangers around. And then we move through the for loop one step and we end up in east, and then we move forward one step and we end up in south. The beauty of this method is that it works regardless of which cardinal direction you are in. As long as you are able to track in which cardinal direction you're currently traveling to, you find the left to that direction, run the for loop 3 times, and then fill in the blanks. So let's see how we can do this. The list dangers, or vector dangers, at the position I, 0, 1, or 2, will be equal to the cardinal dangers, which is dangers to our cardinal dangers, which is dangers list in this case, at the index I plus underscore, well, actually it's better to think about it, underscore index, the initial position, plus I, which is given by the loop variable. And then we apply the modulo 4, making sure that it happens after the addition. So otherwise, he applies modulo to I. There it is, I believe. And now we finally return that vector dangers. There we go. Okay, so what else is left to do? So there is a problem here. What's the problem? The problem seems to be in the initialization of the list comprehension. Where is that? Here. So 0, 4. There we go. Okay. Okay, so in the call to the get state, get state, we also need to pass the food. That's an important component. And notice that the state is being called twice. We call self.foods and we pass the index 0. Let's enter the get state one last time, hopefully. And in here, we need to concatenate the different elements that make this list. So let's create a new version of the state and let's make it equal to the cardinal positions plus a list made out of all of the variables related to the food position. Is right, is down, is left, is up. And finally, the vector representing whether or not the dangers are around. And that should total, and that should add up to 11. Let's run the code. Let's see what feedback we get. Hopefully the network can't begin its training. Okay, we have an issue. Oh, of course, I never show how to create evaluate position, evaluate the point. So let's create this method over here. Define evaluate point, and we receive self and a point or coordinate called PT. First, we evaluate if that point is touching any of the 4 different walls. So if the point at index 0 is bigger or equal than the screen at index 0, that means it's over the right edge of the screen. Or if PT at index 1 is bigger or equal than the screen at index 1, which is the last pixel that represents the height of our screen, then is also representing danger. And then we move to the opposite case of the x-axis, less or equal than 0, or PT at index 1 is less or equal than 0. So those are the 4 cases, and if any of those is true, it's enough and we return the number 1. Otherwise, we return the number 0. But there is another situation that we need to be aware of, and that is if any of the body parts is about to touch the head, or better say the head is about to touch the body parts. So we go through every body part in the list self.body at index, well, all of the elements except for the last one. Remember to skip the head, the current head. And then we can ask if, and actually let's access the head once more. I don't think we need the head, sorry about that. We're touching not the head, but the point. that will be the next position of the head, that's when we called collide point, which is a really nice method that lives inside of the Pygame rec components, and that one will be the one receiving that particular point. This will return true or false, and if it returns true, we also give back the digit 1. So that is evaluate points. Let's run the code. Let's see if our agent trains. And this time things seem to be working fine. I'm gonna make 2 last adjustments before we can leave the agent running and see if it trains properly. The first one is in the model.py file, which is the synthetic brain of our agent. This is a lot of complexity in terms of the number of parameters, so we will simplify this. We will reduce 2 of the linear layers along with the relu values. Actually, the last relu doesn't need to go in there, and I guess we can keep one of the linear layers, just remove one. And instead of returning a number of hidden layers that is equal to the hidden size divided by 3 in integer division, we just return the output size. The second change is the click, because I'm about to change the frames per second, and I want it to be, I want the agent to run as fast as it can. I believe that could be it. Let's print at the bottom the total number of games that the agent has played. Oh, sorry about that. And also let's talk about epsilon. I'm going to increase the total number of episodes in which we will allow randomness from 120 to 200. And this to 250. Just to make sure that we give the agent enough time to explore its surroundings, so that by the time we reach the game 200, we are very close to just receiving instructions from the agent. Okay, so at this point, the only thing we need to do is wait, and I'll pause the video and come back in 20 minutes or so to see how the agent is doing. I sidetracked a little bit and forgot that I had the model running while editing this video, and I ended up running it for 1024 episodes. The good news is that the model is working, but it didn't come without any caveats. There was one mistake, semantic mistake, that I made in the state representation that is very important to fix. It happens right here, so it is not obvious initially, but self is referring not to the head of the snake, but rather to the agent's position, which we never even touch. So we need to create a representation of the head by taking the last element in this collection at the index -1, and now we can substitute it by the variable age. So that is now referring to the position of the foot relative to where the head is right now. We can run the model once more, and we could get something that looks more or less like this. At this stage, we can consider our program a success. The model has been trained, and still it gets inside of gaps that it creates for itself, and it gets trapped and it cannot exit. But that is something that we may not be able to fix using deep Q learning approach. We may need to jump a little higher into more sophisticated architectures, particularly recurrent neural networks, and more optimally recently in what is known as long short-term machines. So before we leave, I'm gonna leave you with a treat. So going to the game manager, the only thing we need to do to create another agent at this stage is duplicating the GameObject agent at index 0. We don't even need to rename it something else, and to prove it, I can change the value in here on the position in the y-axis to 8 to move the second agent a couple of body part units down. If I run the program once more, in theory, I think we scale the program correctly. We have a second agent, and each of these agents is doing its own thing. These two agents look exactly the same at this point, however. And something that I like to try is to change their sprites. So I will quickly go to the designer by using the command prompt in my computer, activating my Pygame environment where the RLPP designer is installed, and I can open it. Once the graphic user interface is opened, I can go straight to the agents and press the plus button. I want to access at its resolution 32 the other color that we have for the agent, which is this green one. I will copy the location of this file in my computer, and then I will close the designer. So I can open the folder. I can open the folder and make a copy of this second body part and paste it in my working directory. In here, I enter the images folders and I can paste the new image. I will also need to grab the name of this file inside of the images folder because I'm gonna need it, and then I can go back to the code. For my second agent, I will not be using BP1, I will using the second file that I just copied and pasted, BP2. Let's see if this program works. There it is. And the green snake is doing something a little strange. But let's leave it running and then we can come back. I'll pause the video one last time and then I'll see you in 20 minutes. Okay, after 800 or so generations, we can see the competition between these two types of agents. They have the exact same parameters, but it seems that out of stochastic processes, out of randomness, one of them gets perhaps a little frustrated, it doesn't move, while the other one learns to maximize the resources in its environment. And I think that part of the reason why this happens is because there is only one food resource. However, let's finish the tutorial at this point. I'll see you in the next one.